turn to page 24. Are you keeping up with this? Yeah, okay, I did. So, I'll be on page 24 to 27. So, okay, let me review a bit with graphing, and then we'll finish graphing today, and then we're going to go into test review today, test review tomorrow, and Wednesday. We're going to work through the rest of the review sheets. I have a couple of more review sheets for you to practice with if you would like. I do need to take, let's see, raise your hand if you have a device that you have not tried with yet. So it's our fifth and seventh period. Wednesday is the day that I'm going to take the class down to get device return. So I don't know how long that's going to take, but I know it's going to kind of cut into Wednesday period. So I feel that I know that some students want to take the test on Wednesday. If that's still the case, then you can take it either during your lunch period, if you have a lunch period, fourth period, you can take it fourth period, or you take it before school, okay? But I don't think we can do it in class like I thought we could, because that's the day that so I have to take the class down to the still Thursday. So raise your hand if you have a sense that you may want to take. I'm not gonna ask that you're committing right now, but how many feel like you may want to take the test on Wednesday? That's fine. They can either come before school or come during fourth period and take it during that. So we're pretty good. So, but then that means I can use Wednesday in class to do further review in class. Okay. That it may only be like half the class or maybe 2/3 the class, and then you can take it Thursday during class or right. Take Wednesday before school lunch or Thursday in class. And obviously, if you're not here Wednesday or Thursday, then Friday will be the makeup day. And that should be the final grade. Okay, that's the end of all of our course. Any questions there? Okay, so the good thing is, we covered everything, and now we're just reviewing. So at the end of class, I'll put out the remaining test review sheets. You can choose to pick them up or not. It's fine. But I have them printed out in case you want to grab copies, and I'll have the keys as well as videos on the website for you guys to use this resource. Okay, just help you further prepare. Okay, so just a recap from last week. We're on page 24. We talked about how when you're graphing log functions, we want to kind of target these helpful characteristics. So the first thing is you want to identify the argument. So the argument is the portion that sits inside the parentheses of your log function. Okay. Sometimes if the parentheses is not there, you can kind of create those parentheses so you can kind of target what you're trying to look at or what you're trying to work with. So the first is set the parentheses, which I'm going to call the log argument, equal to 0, and solve for x. And when you do that, you're able to find the vertical asymptote. And that's really helpful. Even though the vertical asymptote is technically not on the part of the graph, it does give you a nice boundary so you know where the graph is kind of beginning. The second property is set the parentheses or figure out what x value will cause your parentheses to be 1. Because whatever will cause your parentheses to be 1, then you know log of 1 is always 0. If that's the case, you get a very clean order pair for you to plot. The third property is figure out what will make your parentheses equal to the base value. Okay, so whatever will cause your parentheses to match the base, that's a really nice property as well, because if I get log base b of b to happen, it could be log base 3 of 3, it could be log base 5 of 5. That's always going to be equal to 1. And then this one is not as important, but it's just good to know. Whatever will cause your parentheses to be the reciprocal of your base, then that property, this value will just become -1. Okay. So let's see if we can practice with continue practice on bottom half of page 24. Okay, we have y equals log base 1/4 of x. Let me rewrite that. Y is equal to and my argument is that x. Okay, so let's set our parentheses equal to 0. And what does that tell us? This is going to be what? If I set the parentheses equal to 0, that's going to tell me the location of my what? Vertical asymptote. All right. So there's no adjustment that needs to be made, right? There's only x inside the parentheses, so when x equals 0, that's just my x value. That's my vertical asymptote. Okay. Next up, what x value will allow me to use this property here? 1, right? It's just as simple as putting 1 in there, right? There's no shifting that's going on here. So log of 1 is always equal to 0. It doesn't matter what the base is, right? It could be 1/4, it could be 8, it could be 10. Okay, so that's my order pair there. What can I do to make this third property work? Use x to be what? What x value can I choose that will make the base and this value match? 4. And what's log base 1/4 of 1/4? 1, right? As long as the base and the value match, that's always equal to 1. And what value can I choose for x that will cause this property to work, to allow me to use? Let x be what? So 1 over b means take the reciprocal of my base. What's the reciprocal of my base? 4. So the reciprocal of my base will cause this value to all be equal to what? -1. So we should have nice order pairs that we can plot. Zero is our vertical asymptote. And the rest of the order pairs, we can just easily plot there, right? So 1, 0, 1, 4, 1. Make our best estimation. It'll be really close to the dotted line. And then 4, -1. So this graph is going downward, and it's because my base is less than 1. So there's kind of a bit of a reflection here if my base is less than 1. Okay, let's gather the characteristics that the problem is asking for. It's asking for domain, range, x-intercept, asymptote, behavior. Okay, what's our domain? Yeah, x values, right? Starts at 0 and it moves to the, it's on the right side of my y-axis. Okay, range. Okay, vertical asymptote. X equals 0. X-intercept 0. Okay. Okay, end behavior. As x approaches infinity, that means as we follow the arrow to the right, where is it headed? Well, the y value. What happens to the y value? Negative, yeah, going down to negative infinity. And as we follow the other arrow, as it approaches the asymptote, what's happening to the y value? Going to positive infinity, yeah. Okay, number 2. Says use the graph to describe the transformations that result in g of x, then sketch both graphs. So let me have you copy this down here. These are the transformations that can occur with any parent function, but for us, we're going to talk about log functions. So if we start off with log of x, okay, let's say that log of x is base 10. It could be base 2, it could be base 3, but here they're telling us that the parent graph is log base 10 of x. It's asking us to describe the transformations that result with this log base 10 when we add these features to our function. So as a review, here are the 4 major transformations that we need to be responsible for or know how to spot or know how to identify. The first is if you see a negative in front. If you see negative in front of the expression, that means there's a reflection of that parent graph. Okay, there's a reflection over the x-axis. Now, there may be a -3 or -5 or -6, but you just have to understand that if you see a negative in a number, don't think of it as a -6 or -5. Think of it as a negative with a reflection, and the 5 is for something else. Okay, so we need to really be able to separate the negative with the coefficient. Okay, and then whatever number comes after that, cover up the negative, and that number is going to tell us whether there's a vertical stretch or vertical compression. And the way we determine that is we look to see, is that a value greater than 1 or less than 1? Again, we cover up that negative. So if it's 1/3, then it's going to be a compression. If it's like a 5 or a 6, anything greater than a 1, that's going to be a vertical stretch. Next up is what happens inside the parentheses. If you see a number added or subtracted within the parentheses, that means your parent graph is getting shifted to the left or to the right. So just have to understand that your signs are going to be opposite of what you intuitively are feeling. So that means if you see a positive, it's going to be shifting to the left. If you see a negative, that means it's shifting to the right. And then there's going to be a number that's outside the parentheses. That is going to be more straightforward. But that number is going to tell you how the graph, where that graph is going to shift up and down. So if you see a positive, that means it's shifting up. If you see a negative, that means it's shifting down. So let's start off with a table of values for this log, because we're going to graph both these functions. So let's do log base 10 of x first. This is my parent graph, right? Okay, I'll put parentheses. All right. Where's my vertical asymptote going to be? My parent graph. 0, right? You set the parentheses equal to 0. What order pair can I start with? Yep. 1, log of 1 will just be 0. What's the next order pair I can choose? 10, yep. Get the bases to match with the value. And if I choose 10, log base 10 of 10 is equal to, okay. And I think this we can also apply for practice purposes. What can I choose for x to get this property to allow us to use? 1 over 10. So 1/10 will give me what? -1. Okay, we'll plot that graph here. One zero, 10 1, 1/10 is -1. So really, really close to the asymptote. This is growing at a very, very slow rate here. Okay, everybody okay with the parent graph? All right, so now let's talk about g of x. Let's talk about all right, so can we identify here what are the transformations that you see with this g of x compared to the f of x? Good, reflection, because you see the negative show up. What else? Good, right too, good. Okay, let's create our order pair. All right, how can I find the vertical asymptote? Yeah, set the parentheses equal to 0. How can I take advantage of the second property? What can I do to make the parentheses equal to 1? 3, right? Because 3 minus 2 equals 1. If I choose 3, it will cause my parentheses to be 1. Now I can have this nice, easy property for me to use. So log of 3 minus 2, log of 1 is 0, negative 0 is still 0. Okay. What can I choose to make this second property work for me? 12, good. Let's try that. 12 minus 2. 12 minus 2 is 10. Log base 10 of 10 is 1, but then there's a negative in front, so I got to make it -1. Okay, so it's going to be a little bit off the graph, but we can kind of just estimate it. We use a different color here. We're expecting reflection. We're expecting a shift to the right. Zero and 12 -1. I know it's a little bit off the graph, but we're going to just try our best at that point. I have it there in green. Sorry if the hole punch is getting in the way of the graph. Okay, let's finish the rest of the page on 25 and we can start our review. Okay, I want us to get really, really comfortable so that, this, we can, because we know that we have to be able to do 2 of these graphs on the test. Okay, does anybody still need page 24? Okay, here's 25. Good. Okay, we're starting off with the parent graph. I like to show the base. Makes it a little bit easier for us to find all the properties that we want to look for. Natural log is log base e. Okay. Arguments, just that x. All right, where's my vertical asymptote? 0. What's my first order pair? 0. What's my second order pair? Yeah, e. If I choose e for my x value, that will cause my y to be what? 1. And yeah, e is around 2.7, a little bit less than 3. And what can I do here? 1 over e. And because e is around 3, just think of 1 over e as 1/3. Okay, I mean, we just have to, this ballpark value is good enough. If I do 1 over e, that will allow my y value to be what? -1. So, we're purposely using these characteristics so that we're not having to rely on the calculator. We can just rely on these properties. Okay.
Do you want us to graph?
Oh, this right here? Yeah, when you graph e a little bit less than 3, like 2.7. So, but you're going to be, between 2 and 3, basically. Yeah. All right, let's get that graph going. And 1/3 is going to be really, really close to the dotted line. But it's consistent with what you would expect from your natural log graph, right? Your graph is going to hug the asymptote until it gets close to the x-intercept, then it's going to go away from it. Thank you. Okay, we're talking about transformations here. Natural log is my parent graph. So what transformations do you see with the g of x graph that we can name? Good. Stretch, vertical stretch by a factor of 3. What else? Good. Shift up. Okay. Let's find some order pairs. Where's my vertical asymptote? Yeah, 0, right? Yeah. Whatever causes my parentheses to be 0, that's my asymptote. All right. What's the first x value I can choose here? 1. Okay. All right. Plug 1 in. All right. Doesn't matter what the base is. Log of 1 is always what? Good. 0 times 3 is 0. Plus 1 is. Okay. What can I choose here? Log base e of e is 1. Okay. 1 times 3 is 3. 3 plus 1 is 4. Right? Last one. 1 over e. Log base e of 1 over e is -1. -1 times 3 is plus 1. Oh, I didn't plot those points today. Okay, can we try 4 and 5 on our own just to see how comfortable we are with finding those order pairs and plotting them? Try number 4 and 5. Let's see where we are. And if we're comfortable with graphing, then we should be ready for our test review. Okay? Let me put the properties up here so you guys can continue to use them. But they're on the board here as well. Okay, number 4, what's our base? Base 10, okay. Set your parentheses equal to 0. Really, I would say 2 order pairs is good enough. If there's a shift, it's hard to find that 1 over b. I would say not worry about it because it's going to be really close to the asymptote. It's not really going to help you see that whole, but it's a good property to use if there's no shift. But if you have the vertical asymptote and it's 2 points on the natural log graph or log graph, you should have a pretty good feel for how the graph's going to move.
How do you get -6?
-6, right? So let's talk about that. We know how to get to the vertical asymptote, right? We set the parentheses equal to 0. Next one is we want to choose an x value that will cause my parentheses to be a 1. What x value can I choose that will cause my parentheses to be equal to 1? -6. And if I choose -6, it will make it log 1. If I have log 1, then I can get that 0 to show. And then the next one is, what can I do to get my parentheses to be matching to be 10, right? Because that's my base. So I choose x equals 3, right? 3 plus 7 is 10. Log base 10 of 10 is 1. So I'm strategically choosing x values so that I can get that easy y value, so I don't have to deal with messy decimals or having to use, our calculator, and we can just use those properties. Yeah, I would say don't worry about that if there's a shift, because then it's not. Yeah, what you would do is you would set x plus 7 equal to 1/10, and you will solve for x. But it's just really going to be really close to the asymptote. It's not really going to be that horrible. But typically, I would say vertical asymptote of 2 order pairs. That's all you need to get a pretty good look of that graph. Okay, let's try number 5. Oh, sorry about this. Okay, so number 5. I know that E is a little messy here, so okay, if I give you natural log on the test, I'm not going to make it shift because it's going to be hard to figure out what base is going to match with that. So this one, I would say, yeah. Right now, just sketch the graph without that second order pair, but I won't give you one with the shift for natural log. Okay, so for natural log, there may be a vertical shift, but it's a little bit harder to find that, make that E, X value equal to E. So I won't give you one quite like number 5. It'll go through those characteristics easier if I give you natural log without that shift to the right. Okay, let's start page 26. Whenever you guys are ready. It'll be front and back. I don't know the number of questions, but it'll just be front and back. So basically, the test review is a lot longer than the test. The test review is like 4 pages, 5 pages, but it'll have one or two of every section that you see on the test review. Yeah, because the second property, trying to figure out what to choose for x that will make x minus 3 equal to e, it's a little messy, and I'm not going to have you do that. So on the test, if I give you natural log, there won't be a shift left or right. So yeah, that's why I didn't put a second order pair, because this is not quite what I'm going to give you on the test. But it's still good to find that vertical asymptote, find that first point, and then list out all the characteristics. Those don't change. Okay, does anybody still need this page? Okay. All right, let's start off with converting from log to exponential form. So remember, the way we convert to exponential form is we start with the base. What's the base? 49. 49 raised to what power? Good. We go in a circle and we come back, right? 49 to the 1/2 is equal to 7. Yep. Try that with number 2 as well. Then we will go in the other direction with 3 and 4. Okay, number 2, what's the base? 10. 10 raised to the equals. Good. So when you go from log to exponential form, your log notation drops out, right? There's no more logs in exponential form. All right. Meanwhile, if we go the other direction, we're now going to be creating a log with this exponential form. Okay, so we know it's going to be a log. So log base what? 3 of, good. We go around the circle as well, and we pick up numbers as we go around in the circle. Equals, good. All right, try that with number 4. Okay. Log base of equals 5. This is fine, but there's another way to write this, right? We can also replace log base e with what? Natural log. So on the test, either way is fine. I just want to make sure that you guys are comfortable recognizing them in either form and going back and forth between them. All right, good converting between forms. Okay, so now evaluating. If you're asked to evaluate, get an equal x to show up, and then just go through converting to exponential form, and things will just become a lot more clear. So let's get that equal x to show up. What's the exponential form? Equals 3 root of 25. Okay, we want to solve for x, but you can see that, wait, what if I just get the bases to match, then I can set the exponents equal to each other. Okay, so 5 to the x is not going to change. I'll leave that alone. 25 is the same thing as, what, 5 squared. If I convert that to 5 squared, I have cube root of 5 squared. What's cube root of 5 squared written as a rational exponent? 5 to the what? Good. 2/3, right? So the exponent is going to be in the numerator, and the radical is going to, that number connected to the radical is going to go in the denominator. So now this becomes a lot easier, right? My bases match. I can just focus on my exponents. X must be equal to what? 2/3. Okay. Try number 6. See if you can make your way to the answer. If I get the bases to match, then I can just deal with the exponent. How can I write 1 over 16 as a exponential function with base 2? Good, 2 to the negative 4. There we go. That's the hard part. Now you can just identify your x value. Okay, we may not even have to go as far as the second step here. What do you know about log of a negative value? No solution, right? We can't have log of a negative value. So we don't have to go through the step. We just can just say no solution. Okay, there's a hidden base. Yeah. And then 0.01 is the same thing as 1 over 100. Start there. It'll be something, hopefully, yeah, at most it'll be by 0.1, 0.01, or 0.01. 0.1 will be 1/10. This is 100th, or 1 over 1,000. Okay, 1 over 100 is the same thing as 10 to what power? Good. Okay, I want to remind you a couple of properties here before we get to number 9. If I have log base b of b to the x, that's just going to be equal to x. So the idea is if I have log base b of b to the x, log base b of b will take each other out, cancel each other out. It's just the exponent that's going to remain, and that's going to be x. Okay. Another helpful property is this. If I have b raised to the log base b of x, that's also equal to x. So here, if I have an exponent that has the log that, if the exponent has a base of a log that matches the base itself, then we can get that to go away, and the only thing left is the argument. So here, number 9, what's an easy, what do you notice here? What property can we apply here? What's that equal to? What if I write it this way? What's log base e of e going to be? 1. So the only thing left is what? The 4. Yeah. Okay, number 10, 9 to the x equals the 4th root of 3. What's the base that I can use on both sides? 3 to the 2x. And how can I rewrite 4th root of 3? Okay, 2x equals 4. Divide both sides by 2. Same thing as multiplying by 1/2. Okay. Now this 11 may seem a little trickier because I'm looking at this saying, okay, I got 2 log functions. They don't even have the same base. So how can I merge them together? Well, what if I can find a way to get things to cancel out? Right. So let's look at this first expression here. What's nice about 3 and 27? Yeah, 27 can be written as what? 3 to the 3rd. So let me rewrite this. Log base 3, and we know 27 is 3 to the 3rd. Okay, I'll leave that alone. 2, I'll leave that 2 alone in front. Let's talk about this log base 5 of 25. How can I represent that 25? 5 to the 2nd. Okay, so I have log base 5 of 5 to the 2nd. Okay. So 3 cubed is 27, right? 5 squared is 25. So I just made those substitutions. But now let's look at from a different perspective here. What do you notice about this log base 3 of 3? What's nice about this here? That's going to go away, right? So the only thing left is going to be what? 3. What's nice about log base 5 of 5? Yeah, so that's left with a 2. Good. And then that times 2, so 4. So it's kind of playing with these properties in a way that will get these, allow us to get these nice things to cancel out. So 3 plus 4, so. Okay. Oh, actually, we're not going to deal with the x because, again, similar to the previous problem, we're going to try to find a way to get that 32 to match with my base 2. 32 is what? 2 to what power? 6. And then I can think of the square root as a rational exponent of what? Square root is 1/2. 1/2. Okay. So it's a little bit messier here, but I can think of this as 5/2. Right. The 2 in the denominator is coming from that radical, and that 5 is the numerator. So now if I can get this to show up, then I can make this log base 2 of 2 go away. I'm just left with 5/2. And 8 times 5/2 is just equal to 20, right? 8 divided by 2 is 4, 4 times 5. And that's a little messier here with number 12. Okay, properties of logs to expand. Let's just finish off this page and then we'll pick up the rest tomorrow, okay? So the idea is that I can separate all these parts using product, quotient, and power. So basically anything in the numerator is going to be separated by plus. Anything in the denominator is going to be separated by a minus sign. So. Oops, sorry, minus. So I separate the 3 from the x to the 4th, from the y. There's one more thing that I can do. Bring the 4 down. Oh, sorry. Okay, 14. I'm going to deal with that 1/5 to begin with. Fifth root is to the 1/5. There's 2 ways you can go about doing this. You can distribute this 1/5 through, multiply every exponent, or you can bring the 1/5 down first, expand, and then distribute the 1/5 through. Either way, you'll get the same answer. I'm going to bring the 1/5 down, but you can also multiply it and make it 2/5, 3/5, and 4/5. So I'm distributing the 1/5 through, as well as separating each of these terms using product property. And then I'm also multiplying the 2, the 3, and the 4 down separately. Okay, can I come around? I'll come around and just check pages 24, 25, 26.